Section 8-2 is the Pythagorean Theorem and its converse. You're probably familiar with the Pythagorean Theorem, but this is the official definition. The sum of the squares of the lengths of the legs of a right triangle is equal to the square of the length of the hypotenuse. Notice in the diagram here, small a, little a right here, refers to the length of the side that is opposite angle A. The small b over here refers to the length of the side that is opposite angle B, and little c over here refers to the length of the hypotenuse. And the hypotenuse is always the side that is opposite the right angle. And here's what you probably know it as: a squared plus b squared equals c squared. The converse just says it backwards. Remember, the converse switches the hypothesis and the conclusion. If the sum of the squares of the lengths of the two shorter sides of a triangle is equal to the square of the length of the third side, then it is a right triangle. So in other words, if a squared plus b squared equals c squared, where c is the longest side, then it is a right triangle. A Pythagorean triple is a set of three non-zero whole numbers that satisfy the Pythagorean theorem. In other words, the two smaller ones squared, when you add them together, equals the larger ones squared. Notice it says whole numbers, so no fractions, no decimals, no radicals. And here are some very common Pythagorean triples: 3, 4, 5, 5, 12, 13, 8, 15, 17, 7, 24, 25. And if you don't believe me, you can actually test some of them out. I don't expect you to memorize these, but if you're familiar with at least the first two, sometimes problems are a little bit easier. This is the Pythagorean Inequality Theorem. Actually, there's two of them. If the square of the lengths of the longest side of a triangle is less than the sum of the squares of the lengths of the other two sides, then the triangle is acute. Okay, that's really wordy. In other words, if you take the longest side and you square it, and that is less than the other two squared and added together, then triangle ABC is acute. Maybe one way to imagine this is, suppose I were to take side A here between B and C and kind of move it to the left and make it into a right triangle, then this side here would be the hypotenuse and C would get longer. But since C is shorter than the other two sides squared and added together, that means that angle C is going to be an acute angle. And then the same thing applies here. If that third side squared is greater than the other two squared and added together, then triangle ABC is obtuse. In this case, angle C is an obtuse angle. Imagine this side here with the A on it. Imagine it moving up to the right to make a right triangle. Then this side C would get shorter. So if C is longer, then big angle C is going to be an obtuse angle. Let's try some problems here that use the Pythagorean theorem. This is a right triangle. Oh, and perhaps I forgot to mention this. A and B are interchangeable, but they have to be the legs. Notice the legs of the right triangle make the letter L. That's one way to remember it. So to find x in this case, I can do x squared plus 9 squared equals 15 squared. And the hypotenuse always has to be C. So x squared plus 81 equals 225. Subtracting x squared is 144, and x is 12. Here's one with fractions. So again, it doesn't matter if x is a or b, or if 4/9 is a or b, but 8/9 has to be the hypotenuse. So x squared plus 4/9 squared equals 8/9 squared. X squared plus, remember to square a fraction, you square the numerator and square the denominator. So that's 16 over 81 plus 64, equals 64 over 81. And subtracting, oops, I forgot the squared there. Subtracting And no need to freak out, the denominator is the same. Gives me 48 over 81. And when I take the square root of both sides, it's going to give me the square root of 48 over the square root of 81, or the square root of 48 over 9. And if you simplify the square root of 48, you get 4 square root of 3 all over 9. The next problem says, determine whether the set of numbers can be the measures of the sides of a triangle. If so, classify the triangle as acute, obtuse, or right. So remember back from, I think it was chapter 5, the two shorter sides added together have to be greater than the third side. And in this case, that is true. 16 is greater than 14, therefore, yes, it is a triangle. Now, is this a right triangle? Is it acute or is it obtuse? Well, the question is, does it work in the Pythagorean theorem? Is 14 squared equal to 4 squared plus 12 squared? Is 196 equal to 16 plus 144? It is not. In fact, 196 is greater than 160. And remember from the Pythagorean inequality theorems, if c squared was greater than the sum of the other two squared, then it is an obtuse triangle. And here's our last example. Determine whether triangle XYZ is acute, obtuse, or right for the given vertices. In this case, we're not given the lengths of the sides, so we need to use the distance formula on each one of them. So the length of XY is, I'm going to take a shortcut here. I've already calculated it. It's a square root of 8, which is approximately 2.8. The length of YZ is the square root of 2, which is approximately 1.4. And the length of XZ is the square root of 10, which is approximately 3.2. The reason, and actually it's kind of obvious in this case, but it's always a good idea to take your square roots and come up with a decimal approximation, because I really need to figure out which one of these is going to be the longest. So if this is a right triangle, then XZ has to be C. So is the square root of 8 squared plus the square root of 2 squared equal to the square root of 10 squared? And obviously, remember the square root of 8 squared is 8, square root of 2 squared is 2, and so yes it is, and therefore since the two shorter sides squared and added together equal the longer side squared, it is a right triangle.